Hello everybody, welcome back to our virtual fluid mechanics experiment. This second experiment is going to be investigating how fluids exert forces on solid surfaces.
Right. So we've spent quite a bit of time talking about this in the context of hydrostatics, right? When fluids are unmoving. And hydrostatics is this hugely powerful tool that we use to calculate things like the forces on dams, this being the Grand Coulee Dam, one of North America's largest hydroelectric power producers. So we know if we have a dam that's restraining water and that water is not moving, then we can write the pressure distribution using the hydrostatic pressure gradient. And it's fairly easy, this method, to find the total force on the surface of the dam. However, if we lift that dam up a little bit and turn it into a gate,
you could be tempted to use hydrostatics here, right?
Right.
So you determine the forces that are acting using the triangle of forces.
So in this case, however, we have streamlines that begin pretty far apart, indicating a slow-moving fluid squeezed together to show a fast-moving fluid as the water passes underneath the gate. And as Ricardo mentioned, to find the force exerted on the gate by the water, we might be tempted to use hydrostatics. In fact, many people will try this for the first time. But is this correct?
That would be wrong. That would be wrong. The reason being that the fluid is moving in the interface of the gate, and that's going to create a differential type of pressure that we know from our well-studied by now Bernoulli equation.
That's right. Remember, hydrostatics are purely that, static. As soon as the fluid is moving, we have to turn to fluid dynamics, the fundamental equation of which is often cited as the Bernoulli equation here. So to find the force on the gate, when we have the fluid moving and therefore reducing the pressure, we need a way to find that pressure more directly.
Yep. So you can do several things. If you were able to solve what the velocity is at any point in the fluid and right at the gate, you could calculate explicitly what this shape is. That is usually complicated to do.
That is. A simpler solution involves some instrumentation known as manometers, or in this case, piezometers. So shown here is a set of two columns filled with water, each attached to a tube located at a different point in the flow. The upstream tube here is located where the flow is pretty slow moving and the streamlines are straight. The tube here is inserted into the gate, and we can see that the height of the two columns of liquid is a little bit different. If we define the geometry of the problem a little bit more precisely by saying, for example, that upstream the water is a depth of y naught, that the pressure tap, as this is called, is located a distance of y pti for the ith pressure tap above the bottom of the gate, and that the bottom of the gate is in turn a distance b from the bottom of the flow, that the height of the water column attached to that pressure tap is hi, and the height of the water column attached to that upstream tap is h naught, we should have everything we need. And it may be interesting to some of you to note that in problems like this, the water column in h naught will actually line up with the water column upstream, because when the flow is moving slowly, the pressure head upstream is equal to the total head of the flow. So by considering the problem's geometry here and simply applying hydrostatics between this point and the height at which that pressure tap emerges into the flow, we can find the pressure at that location given as P of pressure tap I.
Excellent. So this formula gives us a way to calculate the pressure at any point in the surface of the gate. So
that's right.
We can just add a bunch of taps and get ourselves a sense of what the pressure is in different places, right?
And in fact, adding a bunch of taps is precisely one of the methods we'll be using in this experiment. So shown here would be a series of pressure taps at different points along the gate attached to a bank of these piezometers. And by looking at the height of the water column in each piezometer relative to the height of the water column in the piezometer 0, as well as knowing the geometry of our sluice gate, then we'll be able to find the pressure at each one of these taps, which will then give us a distribution that looks something like this.
One thing I want to point out is that here, depending on the number of taps that we use, we're going to get an approximation of what the distribution looks like. And I think this figure makes a good point.
So, as Professor Mantilla noted, this is only an approximation. And as such, when we take this pressure and we integrate it over the surface of the gate, the best we can do is an approximation to the integral. So taking this, this pressure distribution, we may notice that if we connect each measurement with a straight line, we end up with a series of triangles and trapezoids, which lends this to what's known as trapezoid rule integration, where we find the area of each little block and we sum those together. Okay, and the summation of the area under the curve for each one of these blocks will give us an expression that looks like this, which is pretty ugly, we admit, but is very simple to implement once you have pressure measurements 1 through 7, and once you know that the pressure at the free surface and at the very bottom of the gate where the flow emerges is 0.
So this will be our first approximation to that force, and it should give us a pretty good indication of what's the force on that gate.
That's right. So this is one of our data reduction equations that we'll be referencing later on. The second method.
Yep, a second approach would be to use everything that we have learned in our chapters of control volumes. So we can use we can define a control volume for this particular system and use our equations of mass conservation, momentum conservation, and energy conservation to try to figure out what's the force that gate is exerting on the fluid.
That's right. So if we show an ideal control volume here, we can start to lay out how this problem may function. We know we have flow entering on the left through control surface 0, which has dimensions of y0 by a distance w into the screen, and flow is exiting through this downstream control surface at a much higher speed, where this downstream control surface has dimensions y1 by, again, the width w into the screen. Now, with control volume analysis, we always want to start out by doing a free body diagram of the control volume itself to figure out what forces are acting on it. So we can start to look at that here. So shown on the left is a representation that, in fact, there's a hydrostatic pressure gradient pushing on the contents of this control volume from the left. On the right, we have a smaller but still hydrostatic pressure distribution pushing upstream on the control volume. In addition to this, we have the force exerted on the water by the gate, right? This gate has a reaction force, which is shown here. And summing these together, we can say that these are the three forces acting on the control volume in the x direction. So we can then apply the conservation of linear momentum to the control volume to say, hey, once we know the sum of the forces on the control volume, we can write it as the rate of change of the momentum of the system, or a little bit more simply, the difference between the momentum flux leaving our control volume and that entering the control volume from the downstream end. So simply by knowing the speed, the height, and the width downstream, as well as the speed of the incoming flow, the height of the upstream control surface, and again, the width of the channel, we should be able to calculate the total force of the gate acting on the water. And this is the application of conservation of momentum.
Seems like we still are missing some variables if we want to calculate. So we might want to be invoking our conservation of energy in the flow.
That's right. As Ricardo points out, we don't yet know V0 or V1, and really, they're fairly difficult to measure accurately. So luckily, we have two unknowns, and we have two equations still at our disposal. So the first is conservation of mass, right? The idea that the mass of the system cannot change in time. Or as one of my undergraduate engineering professors used to put it, the sum of the ins is equal to the sum of the outs. What enters through the downstream control surface must leave through the upstream control surface must leave through the downstream control surface. And this allows us to write the downstream velocity V1 in terms of the upstream velocity V0 and the ratio of the areas of the downstream and upstream control surfaces.
So now we make use of two equations, the conservation of mass, conservation of momentum, and now we can look at conservation of energy.
So conservation of energy is shown in its full form here, which involves mass flow rates, internal energy, kinetic energy, gravitational potential energy. However, we're going to make the assumptions here that our process is adiabatic, no heat transfer, that the temperature upstream and downstream is the same, and that we don't have any extreme frictional losses. With these assumptions, this entire expression reduces to a much more familiar one, which is the Bernoulli equation. So simply, by expressing or by comparing the upstream and downstream height and picking points located on the free surface upstream and the free surface downstream, we can solve for V0, okay, the upstream velocity. So now we're also going to want a way to verify that our application of these conservation laws is fairly accurate, right? So during the experiment we'll be showing in a few moments, we're going to use a secondary instrument to measure the volumetric flow rate Q so that we can compare this to our application of conservation of mass, momentum, and energy. So we have now the three equations, momentum, mass, energy conservation, which can all be plugged together to express the force of the gate acting on the water in terms of only the width of the channel, the upstream water depth, and the downstream water depth. Of course, we're not looking in this case for the force of the gate acting on the water. We want the opposite. How much force is being exerted on the gate by the water, which is simply the opposite of this force, the reaction.
Okay, so that gives us our new data reduction equation for this experiment. Right. So we're going to be out there, we're going to be measuring this depth with as much precision as we can, and then we're going to use that to determine the force on the gate. So now we have two independent ways to determine that force, using control volume analysis in our formulas here, and using the integration of the pressures that we measure along the gate.
So now we'll go ahead and enter the advanced measurement lab where we have our flume and move on to the experiment.
All right, so let's move on to make some measurements.
So we're here in the advanced measurements laboratory where we're going to be using the recirculating flume behind me to conduct an experiment involving conservation of mass, momentum, and energy. So this flume has the flow moving from the left end of the frame to the right end of the frame, which is circulated by a large pump which sits beneath the flume's channel. In line with that pump is connected what's known as a mag flow meter, which measures volumetric flow rate, and we'll discuss a little bit more in just a moment. In the middle of the flume is what's known as a sluice gate, which is a partial dam mounted on a track with a crank that allows it to be raised and lowered. Upstream of the sluice gate, the water level is relatively high. The water then passes beneath the sluice gate, emerging as a very thin but high-speed jet or layer of fluid that then develops into what's known as a hydraulic jump further downstream. There are a total of 7 pressure taps, which are penetrations through the sluice gate's thickness, which are then connected to these 7 tubes, as well as one tube located out here where the flow velocity is very small. So shown on the back of the gate here are 2 important things. The first is the linear rule, which is adhered vertically to the back of the gate, which we use to measure the size of the opening at the bottom of the gate. The location of the top of this block lines up with the linear rule at 5 centimeters currently, indicating that there's a 5 centimeter gap beneath the floor of the flow channel and the bottom of the gate. Closer to the center of the flow channel, you can see a total of 7 brass tubes, which are numbered 1 through 7. These correspond to the pressure taps at different heights, which you can see by the 90-degree kinks in each of the brass tubes, and which correspond also to the bank of 7 piezometers discussed earlier. This one upstream tube and the 7 pressure taps are then connected to this bank of manometers, or piezometers.
Yep. So the piezometers are going to allow us to measure the pressure at different elevations in the gate, and they are going to be the information, provide the information we need to calculate the forces acting on the gate. We have one of the manometers is connected to a tube that is upstream from the gate. So what we expect is that this manometer is going to be giving us a reading of pretty much the elevation of the surface upstream from the gate. As we move into the manometers connected to the gate, you see here that there is a difference in the pressure that is being measured as we go lower into the gate. And what's happening here is that the total energy is being expressed as a pressure in part, but this difference between the pressure in the last manometer and the first manometer gives us the velocity head. Finally, we will be keeping our lab view open, monitoring the stream flow that is moving through the flume, and we'll keep close watch on that.
So as we introduced, this is really 2 separate experiments, both measuring the same thing. Our objective is to find what the force exerted by the water on our sluice gate is. The way we're going to do this follows 2 completely different paths of inquiry. The first is using our bank of piezometers and our pressure taps to measure a pressure distribution, which will then be integrated over the surface of the gate to produce a force. To do so, we simply leave the sluice gate in its current configuration and use the elevation in each of the piezometers to measure the static pressure at that location, which will then be integrated using a trapezoid rule.
So our manometers here are set up with a vernier scale that will allow us to measure the water elevation in feet with up to 3 significant digits of precision. So what we're going to do, we're going to start making our measurements for tap 0, which is going to give us the total head of energy available. So we want to make sure that the measuring line lines up with the bottom of the meniscus that is forming inside the piezometer. I think I got that. And now we can measure the height here. So I am measuring 1.728. The idea now is to repeat the same measure for all of the manometers. So let's go to the last one. Again, we're right at the bottom of the meniscus. So here we have, my measurement is 1.326. So the idea is to record each one of the elevations, and we will use those measurements in our data reduction step.
So besides the approach of measuring pressures and integrating them over the gate, we have at our disposal control volume analysis, which will allow us to calculate the force on the gate using only 3 measurements. the depth of the water upstream of the gate, the depth of the water downstream of the gate, and the width of the flume. So drawn onto the side of the flume here is our control volume that I showed earlier. And we recognize that flow is entering the control volume with a relatively low speed, V0, while this control surface has a height of Y0. Downstream from the gate, we have a much smaller control surface through which the flow exits at a much higher velocity, which we're calling V1, through a much smaller surface with a height of Y1. Just as before, we'll obtain the depth upstream using the linear rule adhered to the side of the flume, which gives us 49 centimeters. The width of the flume is likewise, again measured using a measuring tape, showing 24 inches. And the measurement of the water depth downstream is obtained using this needle gauge, which can be raised and lowered, and current to indicate the distance of the tip of the gauge measured from the bottom of the flume. Presently, the gauge indicates 0, showing that the tip is touching the bottom of the flow channel. As we raise it, we will be able to tell when the tip is simply skimming the surface of that sheet of water coming out from underneath the sluice gate. And we can use the vernier scale to once again read out the location of that gauge's tip to a very high degree of precision.
So we're going to make sure that we're going to measure exactly the location of the surface of the water. For that, we can move our measurement tool here down. There you go. That went a little bit too far. That's exactly where I want my measurement. So what I measure here is 0.105. Let's do one more measurement here to make sure that we are measuring within our precision limits. So again, I want to make sure I'm hitting the surface. It's too far. I think that's just perfect. So here I can read 0.104, and that's in feet. So this is a measurement that we want to do 3 times. So let's do it again. There, hit the water. I think I'm right where I want to be. So my reading again is 0.104.
Welcome back from our sluice gate experiment. We're going to spend a few minutes talking about the data reduction, data reporting, and what to expect from the uncertainty analysis. So you may recall there were 2 methods we were using to calculate the force of the water on a sluice gate. Let's start by talking about the first of those methods, which used pressures.
Yeah. So on that method, we make measurements of the water elevation in our piezometers. And we also have measurements of the separation between the place in the gate where we made our measurements. So we use those measurements to combine into our data reduction equation, which was this kind of sausage-looking equation, but it's nothing but a sum of pressures multiplied by an area of the gate. Here, the width of the gate makes another one of the measurements that we need there. So with this equation, we will be able to determine how precise of a measurement of force we can make by determining how precise measurements of pressures we have.
Right. As with any data reduction equation, if we take the partial derivative of this result with respect to one of our measured variables, then we'll get a sensitivity coefficient, which we can use then to propagate elemental uncertainties in, for example, our piezometer water column heights into our final solution here. So let's talk about the second of the two methods, which involved control volumes. Now in this case, we made a smaller number of measurements, only the water depth upstream, the water depth downstream, and the width of the flume. And then by applying conservation of mass, momentum, and energy, we were able to calculate the force exerted by the flowing water on the gate, which was equal to the reaction force of the gate on the water, given by this expression here, which again involves only W, the width of the flume, Y naught, and Y1.
So that gives us, that's our second reduction equation.
That's right.
Here again, we can use this formula to take partial derivatives with respect to the two variables that we have some level of uncertainty, that's Y naught and Y1. We repeated those measurements during the experiment also.
So the real reason this equation is so much simpler than the one involving pressures is because we used that theory for conservation laws to start to knock out unknowns that were present before we applied conservation of mass and energy. The other thing we'd like to know is how correct our application of, say, conservation of energy really is. So you may recall we used an instrument called a mag-flow meter to measure the actual volumetric flow rate through our sluice gate electronically. Now, we'd like to compare this to the result that we get from our control volume analysis. So using our conservation of energy expression, which gives us V naught in terms of the difference in elevation between Y naught and Y1, and saying that that V naught can be turned into a calculated volumetric flow rate by multiplying it by the cross-sectional area, Y naught times W, of the upstream control surface, we can ask ourselves, does this calculated volumetric flow rate match the one we measured using the mag flow meter?
Mm-hmm. So we can summarize our sources of uncertainty. In this case, they are going to be bias limits on the observations that we made on this table. Can you give us a sense of what is, for example, our bias limit on our downstream water depth measurement?
Yeah. So recall that the bias limit, again, usually comes from the instrument itself. And we're not talking about precision limits yet. So the downstream water depth, you may recall, was measured using that needle gauge, which we'll go ahead and write as needle. That needle gauge was equipped with a vernier scale that measured to the third decimal point in feet, giving us a resolution of 0.001 feet. And taking half that resolution as our estimate of the bias limit, we end up with 0.0005 feet as our value of B sub Y1.
So you guys will be able to determine the resolution. You can fill out this table with the resolution of the different instruments that we use, and we can use data reduction and uncertainty propagation equations to determine how these bias limits propagate into our estimate of force.
Now, we're focusing a lot on the bias limits here, and the reason for that is that this problem, we know that it happens to be dominated by the bias uncertainties. The repeatability of the experiment is actually quite good, meaning that precision limit is very small. You may remember that Ricardo measured the downstream water depth using the needle gauge 3 times, right? With differences that varied by less than 1,000th of a foot.
So yeah, so those differences that I made, I would say that there is very little human error or random error that can be introduced into the measurements of length. So this is an example of a problem where uncertainty is dominated by the bias limit of the instruments we use.
So just as in previous analyses, the task is left up to you to find your sensitivity coefficients from the data reduction equations and to propagate those elemental bias limits through to the final answer. Once you do so, it's useful to present your data in a summary table like this.
So here we did 3 measurements of the elevations. We repeated the exercise 3 times.
At different flow rates.
At different flow rates. And for each one of those, we measure the variable y1, the upstream depth, the downstream depth. We had a flow that was measured by our
mag flow meter.
We have our calculated, and on this table we have a ratio of these 2 measurements, because that's going to give us a sense of how good our assumptions, the assumptions that we made on our conservation equations hold. And finally, we can write down the readings that we made on the 7 manometers that we had set up at the gate.
So all of this really is documentation of the intermediate calculations. What we really want to see in this table would be then the force exerted by the water on the gate calculated using each of the 2 methods. And this table is simply a good way of keeping track of your calculations as you carry them out. So this column would give you the force calculated using the control volume analysis, and this column using the integration of pressures. And ideally, we would have very close agreement between the left column and the right column for each row.
So I think with that, and that concludes our experimental setup. And
if you guys have further questions, again, feel free to email myself or Professor Mantilla. We're happy to help you out.